For joining today. Let me first acknowledge the traditional owners of the land, the Wurundjeri people and from the Kulin Nation and the elders past and present. It is a great pleasure to have Greg here, an eminent tropical cyclone and regional climate specialist from NCAR, and our local expert, Professor Kevin Walsh will introduce him in more detail in a second. If you read today's topic, it's also about how tropical cyclones influence climate. This is, you might first think, well, this is the wrong way around. And we also have a PhD student here who does research into how the Great Barrier Reef via aerosol emissions influences the climate. So it's both kind of a similar interesting twist, sometimes what is the interest of scientists. But again, tropical cyclones are so fundamental to climate change. 80% of the damages in 2017 that were weather and climate related, according to the Munich NatCat database, were due to tropical cyclones. So it's a great pleasure to have Greg here today. We have the tropical cyclone expert here at the University of Melbourne, Professor Kevin Walsh, introducing Greg, and thank you so much for coming.
Thanks, Malte. So many of you will know Greg either personally or by reputation, and Greg's had a really wide-ranging career from his days also at the Bureau of Meteorology and later at NCAR. And when I say wide-ranging, I mean across an entire spectrum of meteorological events, ranging from short timescale stuff up to very long timescale phenomena along the lines of what he's going to be talking about today. So his current interests are regional climate prediction, hurricanes, and also the applications of extreme value theory and their relationship ultimately to impacts. So he's currently chair of the Regional Climate Prediction Program at NCAR, and he's also is a fellow of the American Meteorological Society, which, if you know the AMS, that's an extremely competitive process to go through. So he's also had a number of contributions to international policy fora through WMO, and also is lead author of the US Climate Change Science Program report, Weather and Climate Extremes in a Changing Climate. So thank you very much, Greg.
Thanks, Kevin. Sorry, let me go back here just a second. Every time anyone reads that up, I sort of think, oh yeah, that's pretty good. But then I've been around several decades, and to be quite honest, mostly what I did was something that looked like interesting and fun. And some of it turned out quite well. I do have to update my CV, whichever CV you got that from, because I'm actually no longer chairperson of anything. I'm actually emeritus, and I love it. That means I don't go to meetings unless I want to, and I can play with the grandkids when I want to, and I can do research when I want to, and that's about the best thing a scientist could ask for. So today, the title I originally passed on was How Tropical Cyclones Influence Climate and Are Influenced by Climate. It turns out we've gone a fair way in this part of it since I actually sent that abstract in, so I'm mostly going to be talking about how tropical cyclones influence climate. So I'm going from small up to large, and yes, it's actually I think it's held us back a fair bit because there's been this sort of view that systems like tropical cyclones really can't have much of an influence because of their transient nature. They only occur in certain times of the year and everything else. But encountering that, what partly started me down this process was that I read a paper several years ago where, did you know that there is an area in Northern Africa, a very small area in Northern Africa, which if it wasn't there, the Amazon rainforest wouldn't be there. And if the Amazon rainforest wouldn't be there, then the climate would be quite different. And it's because dust from there provides the minerals that are needed and necessary for the Amazon rainforest to survive. trouble with rainforests is that they leach it out very quickly. Anything that's in the soil gets leached out very quickly, and they need this to even survive. And that's what sort of got me to the point for saying, well, don't be saddled by big and little. Go ahead and see what it shows. So the question that has been around, and we've had various discussions over in pubs in the last 50 odd years, is why are there consistently about 80 tropical cyclones globally each year? And that's just the global on the top left and all the various regions and hemispheres shown down there. It doesn't matter where you go; they're pretty constant in each region. The sudden uptick in the Indian Ocean, North Indian Ocean, is because people started actually writing down their observations. And there's been a whole bunch of sort of half-hearted discussions, half-hearted theories that come out on that, but this is the one that we've been pursuing for a couple of years now, and that the consistency is a direct result of the annual number of tropical cyclones being decided by balance requirements for the subtropical energy budget. And I've put sub in brackets there because I don't want to get hung up on a definition of tropics and subtropics, right? I'm talking about somewhere around plus or minus 35 degrees of latitude. And you'll see exactly why I say that in a little bit, because it varies depending on where you're at. I also, during the talk, will talk about the amount of energy the tropical cyclones pump into the Hadley circulation as well. But here I'm talking about the subtropical energy budget. The way I'll go through is an overview of the energy budget, or how it works, the tropical cyclone contribution, the time and spatial scales, which are actually quite large, and then I'll have just one or two slides at the end on the anthropogenic climate change impacts on tropical cyclones and the impacts more that tropical cyclones have as a result of anthropogenic climate changes. And so basically, those of you who've heard me talk about this before will have heard a little bit of the tropical cyclone contribution. That's been expanded somewhat. The third dot point is all brand new, and the bottom bit is also brand new. And the top bit is just meteorology 101. But one thing I want, you actually have to understand how energy gets transferred around in the tropical atmosphere. And so I'm sorry if you find this a little bit old hat and boring, but you have to understand that or you're not going to get the rest of the talk. So I'll spend a little bit of time there to start with. Let's start with the large scales. This is the global radiation budget for the world from Trenberth. And basically we've got a certain amount of energy coming in from the sun. Some of it gets moved around in the atmosphere or scattered from the atmosphere. Some of it hits the surface. That heats up the surface. You get a long wave radiation going back up. That hits the greenhouse gases and comes back down, or some of it comes back down, some of it manages to get all the way through, and then some of it is sent out. And if you add all those numbers in all of those arrows up, you end up with about somewhere around 100 watts per square meter left over, and that's handled by both sensible heat transfer up into the lower atmosphere and by latent heat, which of course can push it up into the high atmosphere. So that's the area we're looking at. We're going to take all the rest for given, and we're only looking at that little area there. And before I go too far, that says 169. You'll hear me quoting 210. The reason is that that's the globe, and I'm only interested in the tropics, and because they're warmer, they cool. They've got a larger cooling factor in the overall process. And I'll also come back to this at various times, but I just want you to understand that the clear air where all of this is happening is about 65% of the tropics. People think of the tropics as being full of clouds. They're not. They're actually, clouds are in a definite minority in the tropics. Yeah, I've got another point, but I'll come back when we get a little bit further down. So the question, no, I'll go back to this just 1 second, sorry. The question is, how does this energy get up? And how does it get to the point where it can actually satisfy this? And all I can say is that this diagram is extremely misleading in that regard. It's schematic, so you can get away